Hello, dear students. Once again, welcome to this YouTube channel. So, in previous class, we have discussed about the magnetic field on the axis of a circular current loop. Okay. So, the direction of the field is along the axis, and finally, we are getting the expression for the field as mu naught upon 4 pi 2 pi I r square divided by r square plus x square raised to 3 by 2 I cap. Okay, if for n number of loops or number of turns equal ದಲ್ಲಿ n number of turns ಇದ್ರೆ ಒಂದು ಟರ್ನ್ ಇದ್ರೆ that is circumference is 2 pi r ಆಗುತ್ತೆ 2 pi r ಆಗುತ್ತೆ ಇಲ್ಲಿ ಅರ್ಥಾಯ್ತಾ so 2 pi r ಆಗುತ್ತೆ ಎರಡು ಟರ್ನ್ ಇದ್ರೆ 2 into 2 pi r ಆಗುತ್ತೆ so ಹೀಗೆ there are n number of turns ಇದ್ರೆ loops ಇದ್ರೆ now the expression for n number of turns is same as mu naught upon 4 pi 2 pi ni r square upon r square plus x square raised to 3 by 2 I cap. Clear? Okay. And the unit of magnetic field is Tesla. The SI unit of magnetic field is Tesla. Clear? Okay. So now, by knowing about the expression for the magnetic field due to n number of loops of turns. Okay. So now some special cases. What about the magnetic field due to circular loop at the center? Okay, here we can write field at the center means field at O. See, if you want the field at the center means the point P is at O, so simply you can take x equal to 0. Okay, that is by taking x equal to 0 we will get the field is at the center. So by substituting value of x as 0, r square raised to 3 by 2, r square raised to 3 by 2 is r cube. R square raised to 3 by 2 is r cube. So hence we can write field at O B naught equal to mu naught upon 4 pi 2 pi ni divided by r, because this denominator becomes r cube, r square by r cube is r, and the direction is along the axis. This is the expression for the magnetic field at the center of circular loop. Okay, circular current loop. Okay, this is the first case. Now, if this r is very small as compared to x, ಏನಾಗಿದೆ radius of the loop is very small and the distance of the point is too large, or the point P is far away from the center, then we can write B. Okay, here you can write vector form B equal to mu naught upon 4 pi 2 pi n I r square divided by x cube. So this special case is if r is very small as compared to x, and first one is x is 0, then we get the field is at the center as mu naught upon 4 pi 2 pi n I upon r into I cap. Clear? Okay. So this is about the magnetic field, special case of this expression. So let us to discuss the magnetic field, the direction of the magnetic field at the center of circular current loop. Okay. See, consider a circular loop. This one is the center. Suppose the current is in clockwise direction and the plane of the coil is same as the plane of the paper or plane of the board or plane of the screen. So now the direction of the field is along the axis, but there are two possibilities. The direction of the field is towards the observer or away from the observer. There are two possibilities. Let us to discuss the direction of the field in this case. Here what happens, if you go through the right hand classroom, here the current is flowing in this direction and the other four fingers are encircled like this. So other four fingers comes out from the center, and here also you can take the direction is here. So the fingers are coming or emerging out from the center, hence in this case the field is towards the observer, okay, and perpendicular to the board, no problem, because the axis is perpendicular to the board. So in this case the field is towards the observer. Now let us to discuss one more case. So in this case, suppose the current is in clockwise direction. So current is in clockwise direction. So then what happens? The direction of the field. See, here the current is flowing in this direction. So now the other fingers are towards the center. Okay, and here also. See, the other fingers are moving or facing or directing towards the center, and the direction of the field is away from the observer and always along the axis. Okay, you can apply right hand class rule for this side also. See, the fingers are directing towards the center. So hence in this case the field is away from the observer. Means in this case the field is in this direction, and in this case the field is in this direction. Both are along the axis, but the two possibilities. In this case it is in this side. Suppose the circle is like this, in this side in this case, and here opposite to this. So as the direction of the current changes, the direction of the field also changes. Remember. Is it clear? Okay. So this is about the magnetic field due to circular loop at the center and along the axis. Is it clear? Okay. So today we have to discuss Ampere's circuital law. See, Biot-Savart law gives the magnetic field due to current element as mu naught upon 4 pi I dl sin theta divided by r square. Okay, so this Ampere's circuital law stated that the line integral of v dot dl equal to mu naught times the current I enclosed by the closed loop. For a closed loop, we can write line integral of V dot dl equal to mu naught times I. So this one is the Ampere's circuital law. Okay. So now, by knowing about this Ampere's circuital law, let us to discuss the field, magnetic field due to long straight wire carrying current. Okay. See, ಈಗ ನೋಡಿ, this one is the current carrying conductor, long straight conductor. So to find the magnetic field due to this long straight conductor, this conductor carries the current I. Okay, let the point P, which is at a distance d from the conductor. Okay, so now the magnetic field is same at the same distance from the conductor. Suppose the conductor, this one is the conductor, at a distance d, the field is same on this circle. Just you have to imagine there is one closed loop. The closed loop is like a circle. On that circle, the field is same. But what happens? The direction of the field is continuously changing from point to point. Suppose at a distance d, so this is the direction of the field, and here the direction of the field, here the direction of the field. Just for the direction of the field, you have to use right hand clasp rule. See, so like this. So simply the field is surrounded around the conductor like a circle. So this one is the closed loop. You can choose the closed loop. On that closed loop, the field is same. And now you have to choose a small length dl on this closed loop. Okay, the angle between dl and d are same, means 0. So hence to find the field you have to use this Ampere's circuital law. Okay, by Ampere's circuital law, line integral of V dot dl equal to mu naught times I. Here V dot dl means V dl cos theta mu naught times I, and here theta equal to 0. Theta equal to 0 means cos 0 is 1. So simply we can write V dl equal to mu naught times I. So this V is constant, take it outside. So integration of dl is L, and here the L is the circumference of the circle. Okay, integration of dl is mu naught times I. So integration of dl is 2 pi d. The total length is 2 pi d, that is circumference of the circle, equal to mu naught I. So therefore the magnetic field B is mu naught upon 2 pi I upon d. Or also we can write mu naught upon 4 pi. Instead of 2 pi, we can write mu naught upon 4 pi 2i by d, 2i upon b. So this is a very important expression for the magnetic field due to long straight wire carrying currents. Is it clear? And here the field is away from the observer, and here the field is towards the observer and perpendicular to the plane of the board. Okay, so this is an expression for magnetic field due to long straight wire. Okay, now down this. Thank you.